Hello everyone, I'm Onnoy and I'm here to present our paper titled There is More to Dual Than Meets the Eye Towards Better Gauge-Based Text Entry Systems with Multi-Threshold Dual. Dual is the most common selection technique for gauge-based systems. The way Dual works is the user looks or points at the target and stays on it for a certain period of time. Research has shown that Dual tends to be slow and prone to accidentally triggering a non-target. Still, previous work was able to show that with multiple days of training, users can shorten their dual threshold up to 300 milliseconds, resulting in a typing speed of 20 words per minute. Yet, even after extensive training, this speed came at the cost of many unintentional selections, requiring participants to make substantial error corrections. More importantly, there are indications that 20 words per minute seems to be the maximum reachable for dual-based text entry systems. Still, we believe there is more to Dual than meets the eye, as little is known about what factors contribute to the 20 words per minute limit. It is well known that dual selection performance is limited by the need to stay on the target for the whole duration of the dual threshold. For this reason, previous work has explored several different avenues to reduce the threshold. However, there is a gap in the literature as no one has systematically explored at a granular level how components of dual selection time improve with training. To address this gap, we conducted an 8-day longitudinal study where participants typed for 15 minutes per day using a keyboard that has a constant dual threshold of 450 milliseconds. In contrast to previous studies, we kept the dwell time constant throughout the 8 days. We conducted the study in VR using the MetaQuest Pro headset, which has a built-in eye tracker, and we recruited 9 novices to participate in the study. To analyze the data, we chose typing speed, KSPC, and MSDER to evaluate the performance of the constant threshold dual keyboard. Additionally, we further analyzed the data by breaking down dual selection into multiple steps. First is the exit time, that is the time taken to exit the key after it has been selected, in this case R. The next step is pointing at the next key, that is G. Thus, pointing time represents the time participants spend to point to the next key after the gaze cursor has left the previously selected key. The final step is activation. Activation time represents the time taken to activate a key after the first time the gaze reaches that key. However, we further break down activation time into 2 categories. First is on-target time. In the example figure, the moment the gaze cursor enters the key, the dual timer as well as the on-target timer starts. However, due to jitter, the cursor drops off the key and resets the dual timer to 0. This is where the second part of the activation time starts, which we call the drop-off time. That is the time participants lost due to jitter. The participant eventually manages to bring the cursor back to the desired key, which starts the dual timer again and simultaneously restarts the on-target timer. This time, the participant successfully dwells on the key for the whole duration of the dual threshold, selecting G. Thus, on-target time is the whole time spent by participants on the selected key. Then the whole process continues all over again. This whole process, that is the summation of the 4 time components, is, in essence, the total time to select a key. Finally, to better understand how jitter affects selection time, we also analyzed drop-offs. That is, how many times the gaze fell off the selected key after reaching it. In the example, exactly 1 drop-off is shown. Results of our first study revealed that participants' average typing speed started at 11.6 words per minute and ended at 14.8 words per minute. No interesting trend or important significant differences were observed for KSPC and MSDER. For the different components of dual selection, all 7 components exhibited a decreasing trend. In other words, the training made participants faster in terms of exit, pointing, on-target, and drop-off time, and therefore activation and total time, as well as decreased the number of drop-offs. Total time decreased from almost a second to about 4/5 of a second. The highest contributor to this decrease was pointing time, followed by exit time, drop-off time, and finally on-target time. Besides illustrating improvements through training, Study 1 also highlighted challenges and opportunities in dual keyboard design. For example, Although exit time improved with training, further analysis of the first 3 sessions revealed that exit time was longer than 250 milliseconds for 50% of the total selections. Similarly, exit time was more than 300 milliseconds for 20% of the time. This suggests that the naturally longer exit time is potentially why novices make many unintentional selections of the same letter, especially when the dual threshold is short, for example 300 milliseconds. Thus, building on the average exit time and other identified challenges, we then designed two novel dual keyboards for novice users. First is the Dual Threshold Dual Keyboard, or DTD. Here, any key can be selected by dwelling on it for 300 milliseconds. However, for successive selections of the same key, the user has to dwell an additional 200 milliseconds, that is 500 milliseconds. In comparison, CTD requires 450 milliseconds for both initial and successive selections. We further improved the design of DTD and call this keyboard Multi-Threshold Dual, or MTD. Here, the first letter of any word has to be selected like DTD. The system then predicts up to 3 letters based on a word prediction algorithm. These 3 letters are highlighted, enlarged, and assigned an even shorter dual threshold of 200 milliseconds. Additionally, the spacebar is also assigned a further reduced threshold of 100 milliseconds. Regardless of how long it took to select the first letter, successive selections always took 500 milliseconds with the exception of the backspace, just like DTD. Given both DTD and MTD are designed for novice users, this time we designed a much shorter experiment. 15 participants typed 30 phrases, 5 phrases per block in each of the 3 keyboards presented in a counterbalanced order. The data of the first block was considered as practice and was removed from the analysis. Results revealed that for both the overall averages as well as for each block, MTD was significantly faster than DTD and CTD. DTD was also significantly faster than CTD. We did not observe any significant differences between the keyboards in terms of KSPC. However, note that the values are much lower than the previously reported KSPC of 1.18 or more for text entry systems with a 300 milliseconds dual threshold. In terms of MSD-ER, although overall averages showed that participants made significantly more errors with MTD than CTD, further analysis revealed that the difference was only noteworthy in the first block. This suggests that participants were still getting used to MTD. As for the different components of dual, MTD was significantly better than CTD in terms of drop-off time and number of drop-offs. All keyboards were also significantly different from each other in terms of on-target time and therefore activation and total time, with MTD being the fastest, followed by DTD and CTD. We also computed the effective dual threshold across all entered keys. This resulted in a dual threshold of just 234 milliseconds for MTD. In summary, MTD's average text entry speed is faster than previous gauge-based keyboards. Moreover, this speed also involves substantially fewer error corrections than previous work. The computed effective average dual threshold of 234 milliseconds is also the shortest dual threshold ever published for a dual-based text entry system. Finally, and notably, we were able to demonstrate these results with absolute novices who practiced for only 30 phrases. Overall, our results highlight the benefits of using multiple dual thresholds, particularly accounting for the exit time seems to be the key difference in why novice users were able to effectively use a system with such low dual thresholds that were previously believed to be unmanageable by novices. In the paper, we also discussed several future directions that could help to go beyond the current 20 words per minute limit. Please see our paper for more details. Thank you.